Hello everyone, I'm Sadia Rahman from Department of Physics. Today I'll be presenting my work on silicon-rich silicon carbide for efficient solar energy absorption. Silicon carbide is a very popular semiconductor material which has over 200 polymers available. It has a band gap of 2.3 to 3.3 electron volt depending which polymer we are working with. But this is higher than the ideal range for efficient solar absorption, which is around 1.5 electron volt. Non-stoichiometric silicon carbide materials, especially silicon-rich silicon carbide, are tailored to reduce SiC's high band gap and to enhance solar light absorption efficiency. First principle calculations have demonstrated that silicon-rich SiC nanoclusters exhibit structural stability and possess tunable energy gaps. To explore the potential of non-stoichiometric silicon carbide in the bulk phase, we investigated silicon-rich silicon carbide by substituting carbon atoms with silicon within different configurations of silicon carbide using density functional theory. For methodology, first principle calculations are being performed with density functional theory. The interaction between core and valence electrons are treated by projector augmented wave method along with PVE functional for exchange correlation interaction. All the calculations and computations are performed with Vienna ab initio simulation package VASP at the Texas Advanced Computing Center TSC. We are grateful for their support. For our work, we have examined different polymorphs of silicon carbide in its pristine state. Then we fully relaxed those structures and calculated formation enthalpy by using the formula where delta HF is the formation enthalpy, and the first term in the right hand side represents the total energy of silicon carbide, and the second term in the right hand side represents the total energy of silicon per unit atom in its most stable bulk phase times the number of silicon atom present in the unit cell, and the third term represents the same thing for carbon, but here the most stable phase is the graphite. From the table, we can see that all the crystal structure of silicon carbide has similar uh, stability, and from the chart, we can see that after 8H, if we add more layers into it, it has no impact on the structural stability of the structure. Chemical formula of silicon carbide has an N in it, which states that N number of carbons are replaced by N number of silicon atoms in pristine SiC. In our case, we replaced up to 3 carbon atoms by silicon. Silicon substitution leads to an increase in the lattice parameter compared to the pristine structure due to the prevalence of silicon-silicon bonding, which have a longer bond length than silicon and carbon bonding. Our investigation also found that substituted silicon atom tends to stay closely, which results in the lowest formation enthalpy and thus the most stable arrangement. For example, in pristine 8H SiC supercell, 3 substituted silicon atoms in carbon sides yields a lower formation enthalpy when they're substituted closer than when they were placed apart. From the density of the state plots, we can see in pristine 8H SiC, the contribution from the valence band maxima is coming from the form carbon p and silicon p orbital. And for the doped structure, both for one silicon doped on carbon side or two silicon or three silicon doped on carbon side, we can see that the valence band maxima contribution is coming from the doped silicon p orbital. Our calculated band gap for different silicon carbide polymers aligns with the existing experimental and theoretical studies, while also reflecting the known limitation of GGA in underestimating the band gaps. Silicon substitution introduces defect state in the band structure, and when silicon atoms are in close proximity, these states strongly interact. The interaction between closely spaced silicon atoms enhances the overlap of impurity states, leading to a more significant band gap reduction compared to when they are farther apart. And this fact is seen from the band structures from the silicon-rich silicon carbide. First, we see the band gap for pristine 8H SiC, which is 1.78 electron volt, and when one silicon was doped on carbon side, the band gap reduced to 1.20 electron volt. When 3 silicon is substituted on carbon side, the band gap even reduced more and it became 0.95 electron volt. A more non-dispersive and localized defect band is seen near the Fermi level. I would like to end my presentation with few concluding remarks. Our first finding is substituted silicon atoms prefer to stay closely, which leads to the lowest formation enthalpy and the most stable configuration. Second, partial density of state plot analysis shows that the prominent contribution near the Fermi level originates from the p orbitals of doped silicon atoms. Third, the band gap can be tailored by substituting silicon atom on carbon sides in the pristine SiC structures to achieve a band gap value that closely aligns with the existing experimental result. Hybrid functional calculations are currently being performed. Overall, tailoring the band gap by replacing silicon on carbon side in SiC makes it more useful in the realm of SiC-based devices and solar cell applications. Thank you.